Hey, what's up everybody, and welcome to another section of this Algorithmic Patterns course focused on the BFS pattern. In this section, we're going to go over our third problem using the BFS pattern, which can be found by filtering the Leetcode patterns list like so. In this problem, we're asked to find the minimum depth of a binary tree. They go on to explain that the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. A leaf node is a node that has no children. So in other words, they want us to find the node closest to our root node that has no children. So the number of nodes from the root node to the nearest leaf node also happens to be the number of the level that contains the nearest leaf node. For example, our nearest leaf node for the tree in the problem description can be found in the second level of the tree, which is also the number of nodes from root node to the nearest leaf node. So we're going to solve this problem the same way that we solved the previous problem. We're going to search our tree in a breadth first or level order manner until we reach a node that has no children. The algorithm is also pretty much the same as the one we used in the previous problem, so this should be relatively straightforward. So let's get into writing some code. Okay, so in our Python source coding interview patterns directory, we're going to change directory to BFS. And within this directory, we're going to make another directory that we're going to call minimum depth of binary tree. And we can change directory into that directory, and we can create a file called minimum depth of binary tree as well. And within this file, similar to the last two problems, we're going to import collections so that we can use dec as our queue. And we also need to get our tree node class. So we can just change this to Python 3 and get our tree node class as usual and paste it in. And let's go ahead and uncomment the class, and let's create our entry point as well. And this time, actually, instead of writing out the binary tree ourselves, we can just go into one of our previous problems and copy the binary tree from there, because it's the same binary tree in the example for all three of the problems. So the binary tree here for minimum depth of binary tree, this binary tree is the same as the binary tree that we use for average of levels in binary tree. So let's go into that file and go to the bottom here and just copy this binary tree. And then we can just come back to our file that we're currently writing the code for and paste it in there. So now we have the binary tree here, which is the same binary tree here. And from there we can just print the result of our function minimum depth. We're passing in the BT, the binary tree. And let's go ahead and create this minimum depth function. So we'll define minimum depth, and it's going to need to take in a root node for a binary tree. And as usual, we'll start by creating a queue using the dec data structure. And also let's go ahead and check if our root is none. And if it is, we'll just return 0. And we'll start by appending our root to our queue. And following that, we want to create a variable for our depth, or the number of levels that we traverse down our binary tree. So we'll do a variable called level count, and we'll set it equal to 0. And we'll do while length of queue. So while the queue still has nodes within it, we're going to get the size of our level, which is going to be set equal to the length of queue. So this is the number of nodes in the current level, and we're going to increment our level count. And then we're going to start iterating through our current level. And similar to the last two algorithms, we're going to pop the leftmost node off of our queue. And we're going to check to see if this node has no children. Because if this node has no children, then that means that we've reached the minimum depth. For example, if we reach this node 9, we see that 9 has no children, so we can't traverse any deeper. And this is the minimum depth for this tree, because as you can see, these nodes here that have no children, they go deeper than this node here. So minimum depth being, if we were to traverse this tree in level order, the first node that we encounter that has no children. So this is where we check to see if we've encountered that node that has no children. So we say if not node.left and not node.right, then that means we've reached the node that has no children. And if that's the case, we're just going to return the current level count. Because, for example, in this case, if we reach this node and we're on this level is where we first encountered a node that has no children, which means that this level is the level where we encountered our minimum depth. But if that's not the case, we need to check for both nodes left and right. And if either exists, we need to append them to our queue. So if node.left, we're going to queue.append node.left. And we're going to do the same thing if node.right exists. And that's actually going to be it for this algorithm. So let's go ahead and format, and then we can just go ahead and test this. So as you can see here, for this binary tree here, we're expecting an output of 2, because here it says the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. A leaf node being a node that contains no children. So we have the root node, that's one node, and we have the actual node that contains no children, which is 2 nodes. So our output is supposed to be 2, which is our minimum depth. So if we do Python minimum depth of binary tree.py, we can see that we get the result 2, which is the expected result. So now let's go ahead and get into our visualization for this algorithm. Okay, so let's get into visualizing this algorithm, and we'll go ahead and start by drawing out our binary tree. So we'll start with a node here, and it will have a node here, a child node, and a child node here, and the same with these 2 child nodes. And the values at the root, we have 3. Actually, let's do red. At the root, we have 3, and the root's left node is 9, and its right node is 20, and then we have 15 and 7. So for this algorithm, minimum depth, we basically just need to find the number of nodes that it takes to get to the nearest leaf node. So a leaf node is a node with no children. This binary tree has 3 leaf nodes. The one that's closest to our root node, this node here, is the minimum depth node. So in the case of this binary tree, this leaf node here is going to be the minimum depth node, and there's 2 nodes along this path here to the minimum depth leaf node. So at the start of our function, we're going to take in the root node of this tree. So we're going to take in this node, which essentially gives us access to every child node or this entire tree. And we're going to start by creating a queue. So we'll create an empty queue. And then we're going to check to see if root is none. So if root is none, then we're going to return 0. But our root is not none. So we would then go on to append the root to our queue. So we're going to append this root node to our queue. So 3. And we'll start this level count variable. So this level count variable is just going to keep track of the number of levels that we traverse. So this would be 1 level, this would be 2 levels, this would be 3 levels, etc., depending on the size of the tree. And we'd start by starting this while loop that is going to continue to run while the length of queue is not 0. So currently the length of queue is 1. We have 1 item in our queue, so we're going to continue with this while loop. loop. And we'll set the level size to the length of the queue. And by level size, we mean how many nodes are in the level. So the current level that we're on here has one node, this node containing 3. This second level here has 2 nodes. So the level size for this level would be 1, 2. So currently our level size is equal to 1. And we're going to go ahead and increment our level count because we have a level here, so we're going to increment our level count 1. So we can go ahead and write these out as well. So we have level size, which equals 1 right now. And we have level count, which also equals 1 right now. And we're going to iterate through the size of level size. So we're going to basically do one iteration because level size is only 1. And we're going to pop left off of our queue. So let's go ahead and pop it off. So we're going to pop the 3 off of our queue, and then we're going to check to see if this node that we just popped off of our queue is a leaf node essentially, because if a node doesn't have a left and doesn't have a right, it's a leaf node. So we want to check to see if this node is a leaf node. So we're checking if not node.left. So this node's left exists, so this isn't true. And then if not node.right, this node's right exists, so this isn't true as well. So we're not going to return our level count. So we're going to move down to this line of code here where we're going to see if node.left does exist. So does this node have a left node? Yes, it does. So we're going to append this node's left node to our queue. This node's left node's value is 9, or this node's left node is 9. So we're going to append that to our queue. And then we will move down to this line where we're going to check to see if this node's right node exists. So this node does have a right node, and it's this node here. So we're going to append this node to our queue as well. So that's going to be 20. And at that point, we would be done with this 3. And we'd go back up to the top of this for loop, but our level size is only 1, so we're not going to iterate through this for loop again. So we'd go back up to the top of our while loop. And the while loop will continue to run because length of queue is now 2, 1, 2. So it's going to continue. And once again, we're going to set our level size. And our level size is the size of the queue, or the length of the queue, which is 2. So we'll change our level size here to be equal to 2. And our level count, we're going to increment it 1. So we're going to do +1, which equals 2. And actually, let's just write 2 here so it's not so much. So now at this point, we're going to iterate through this for loop for the size of 2 because our level size is 2. And that's this level here that we're dealing with now because these are the 2 nodes that are in our queue. This is the level that we're dealing with now. So we're going to pop our leftmost node because remember, queue is first in, first out. So we're going to pop this node because this is the node that was put into the queue before putting this node in. So we'll pop this node. So we're dealing with this 9. And then we're going to check to see if not node.left and not node.right, which is going to essentially check to see if we are at a leaf node. And if we check here, we see that 9 doesn't have a node.left and it doesn't have a node.right. So that means we do have a leaf node here. And if this condition is true, we're just going to return our level count. And our level count is 2 as well. So we're going to return 2, which is going to be the answer for our minimum depth. Because as the problem description says, the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. So we have 1, 2 nodes from the root node to the nearest leaf node, which also happens to be the number of levels that we need to traverse to get to the minimum depths node. So there's 1, 2 levels, which is the same as the number of nodes along the shortest path from the root node to the leaf node. So if it would make more sense to you, you could actually change this level count variable name to node count or something like that, because they're both interchangeable. They'll be the same thing always. Because even if this node were our leaf node and this node were the one that has these 2 children, so for example, even if it was like this, and this were the leaf node, it'd still be 1 level, 2 level from this node to this node. And it would still be 1 node, 2 node from this node to this node. I hope that makes sense. So now let's go ahead and get into our time and space complexity. So we'll start with our time complexity, which you've probably already guessed is O of n. So in the worst case, we need to touch more or less every node in the tree. So even if we had a tree that looked like this, a fuller tree, we'd traverse this level and then this level, and then we'd get to around this node of this final level, and then we'd find our leaf node, but still more or less we're traversing every node in the tree, more or less. Of course, it's not going to be completely exact, but you get the idea. It's just big O. And our space complexity is going to be O of n as well, because our queue at most would need to hold roughly n nodes. And that's going to be it for this algorithm. I hope that this information was helpful to somebody, and I'll see you in the next one.